Hello. So in this presentation, I want to start a series of a couple of videos, hopefully several of them, I don't know exactly how many, in which I want to make a little bit of a connection between some important mathematical concepts, like definition in this case, with what people encounter sometimes as issues in a debate about other topics, not necessarily mathematically oriented. Now the problem is, of course, the connection between math and real life is not always that obvious, but I hope in the examples that I'm going to give you, it's not going to be that hard to understand why this concept of a definition actually is important. So in this first episode, shall we say, we're going to illustrate with a math example why definitions are important, and then I'm going to make a connection with one or two real life examples when the lack of a definition of the concept makes people to actually not understand each other, or maybe wasting the time in a debate. And on the flip side, when a clear definition actually is agreed upon, usually the conflict of main issues is not that pronounced, and people tend to come to a common ground, although of course debates can still happen around the common definition of the concept. So for this presentation, you should be exposed hopefully to Calculus 1, although it's not actually that strictly necessary. Calculus 1 and Calculus 2 are probably better as prerequisites of what I'm going to talk about. In fact, you're probably better off if you didn't study at Calculus 2, because then I think the point I'm trying to make will be more interesting. Because once you actually finished Calculus 2 and you know everything about it, like series in particular, then you would understand immediately that where I'm going to go with the argument. Okay, so suppose, for example, we have two students that want to discuss a topic, a mathematical topic. Let's call one student Bill and the other one Joe. I know, not that inspiring names, I guess, but these are the default names. I always think about Joe Doe when I read Joe, but let's call them B and J, Bill and Joe. And let's suppose that the two students want to figure out how to discuss this topic of an infinite sum, right? So I mean, they want to, via an example at least, figure out how to define the addition of infinitely many numbers, what we call in Calculus 2 series, right? So, and they start with an example. Well, let's write it actually in the generic case, right? I mean, this notation, if you're not familiar with, stands for A1, excuse me, not A1, A2, dot, 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 an, and so on. So n, going from 0 to infinity, is simply an index to indicate in a short notation that you want to add infinitely many numbers. If I had here a precise number, this would be an infinite sum, right? I mean, people sometimes write, of course, infinite sums using the same sigma notation, right? So this will be just a naught plus a1 plus a2 plus a3 if you start from 0. But how do I add infinitely many numbers? And suppose the two students in our story start with an example, or they start with more examples, but let's say they stumble upon one example where they have some disagreement on how to proceed. So for example, they want to figure out how to add these numbers in a series, -1 to the n from n equals 0 to infinity. And again, remember, this stands for -1 to the 0 plus -1 to the 1, dot, 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 and then so on. And of course, the exponent alternates between an even or an odd number, so this becomes what we're going to call in Calculus 2 actually an alternating series. So 1 minus 1 plus 1 minus 1 plus 1 minus 1, so on and so forth. And then here comes the misunderstanding or the debate, right? So the Bill says, okay, I'm going to take this infinite sum that you wrote above there. Let's write it again here. And because I know addition is associative, nothing stops me, and it's perfectly reasonable to associate the terms 2 by 2. If I have infinitely many terms in the summation, obviously I have infinitely many pairs that I can associate this way, 1 minus 1 plus 1 minus 1 and so on. And then of course I can compute this operation in each parenthesis, and any sane person would agree you add nothing infinitely many times, you end up with nothing. Okay, so 0 plus 0 plus 0 is equal to 0. So then Bill declares that the summation of the series is equal to 0. On the other hand, Joe disagrees. Joe wants to do it slightly differently, though pay attention here, it's not that far off from what Bill did. Bill claimed that, I can associate numbers however I want. Joe essentially says, it doesn't disagree fundamentally, but he claims that, okay, I'm going to do the same, but I feel like saving the first term, 1, and then grouping the rest of the terms 2 by 2 just like you did, but starting with the second term in the series. You can do that, then you end up again with infinitely many terms, infinitely many parentheses, each of them equal to 0. So then, from Joe's perspective, then the summation is 1 plus infinitely many zeros added to it. Infinitely many zeros added to it amounts to nothing, 1 plus 0, and then Joe claims that the series is equal to 1. Now again, this is why I told you that if you took calculus 2, that's not so fun or interesting maybe at this point. But, because you know the answer, right? And I'll give the answer immediately. But pay attention here, the issue is not the fact that they don't know calculus 2. Nobody actually is required to know calculus 2, right? The issue is that by not knowing calculus 2, they do not have a working definition of what they are talking about. Okay, so they're talking about infinitely many numbers added together, which is a completely unknown concept. And you use your intuition, and of course with just the intuition you can have different answers if the way to approach the problem, or the working definition if you want, is different than your debater. None of the two guys here are really guilty of anything, and they may make perfect sense with the math they know up until this point. They simply lack a common ground, a definition of what they're talking about that they can agree upon. Because the debate can still happen. So once we agree that we talk about a clearly defined concept, then we can, of course, disagree, and then usually in math cases, a proof is the resolution, right? There's going to be one answer to a specific questions, or the other. Usually it's not ambiguous, right? Once you have a clear definition and a bunch of properties that you agreed upon. So in case you didn't take calculus 2, before you actually talk about examples like this, one defines strictly what an infinite sum is, right? So if you have an infinite summation, the sum of it, the infinite sum, is defined strictly via a limit. So we say that an infinite sum like this one exists if the limit of the so-called partial sums, which means adding the first n numbers, or n plus 1 in this case, because I started the count from 0. This is called a sequence of partial sum, usually it's denoted by Sn. So if this exists, then this limit constitutes the summation. So no matter how much you want to play around with the association here, like Bill and Joe did before, the common ground in mathematics, or the common agreement in terms of the definition of what an infinite sum is in this context, is this limit. If this limit doesn't exist, doesn't matter how much you wish to play around with these numbers, it simply means the summation doesn't exist. So there is no such thing as an infinite sum if this limit doesn't exist. So then if we go back to the examples we talked about here, we can clearly see that if you take the sequence of partial sums, so if you add a 1 minus 1 plus ... minus 1 to the n, well, again, I started the count from 0. That means this is going to be either 0 if n is odd, and 1 if n is even. So we know from calculus 1 that in this case, obviously, the limit, so if this is Sn, the limit of Sn as n goes to infinity does not exist. And so obviously then we don't have the concept of an infinite sum in this case. Okay, so how does that translate with real life issues? Well, I'm going to illustrate with two real life examples in the second part of this presentation. So, because I don't like to waste time erasing the board in between takes. So stay tuned for the second part.